Okay, now it's being recorded. Everything here is being recorded. So where's it all going? Okay. Chemistry with Dr. Smith YouTube channel. So you can Google Chemistry with Dr. Smith or go to YouTube. But anyway, it's right. Just easiest way is just to Google Chemistry with Dr. Smith. Right? Then it comes up and okay. Now you can become a subscriber. Advantage of that is every time when I put it up then, and it goes there. So 24/7 you can see what's going on in this class. If you miss it, sport, wedding, sleeping in, whatever. Now there's a lot of stuff here. So what you do is you just click playlist, and it straightens it all up for you. Recognize, there you are, Chem 4431 Fall 2012 PChem. Okay, there's 2 videos. That's not right. It's still updating itself because I had to remove one. There's no sound. So this is day 1. All right, so you click on it, and advantage to this is you can scroll. Let's see. Oh, did I stop it? I can make it a lot louder, but I took it out. But the point is you can, when we hit a problem, you can kind of actually scroll down and let the words get scribbled in there. So if you don't want to listen to that nauseating voice in the background, just drag it and you can see solutions get done, right? Or how do I do that number 7, right? Just you can go fast forward to it. Now, this research has shown is a support tool. And what folks have found the most useful for academic podcasts like this are to sit where you're sitting, and then you use this as a support tool. And that's its biggest benefit. Okay? And it's new, but that's what research is finding. So it's interesting. So, but especially the guys in sports, I think. They don't have any choice. That would be this one. Okay, so Chemistry with Dr. Smith. Let's see. So here we are talking about gases and property of gases, and we left off with the ideal gas law. And Rob, what was the problem with an ideal gas? Like what?
Technically would have to have infinite volume, not be able to make collisions.
No volume, can't collide because there's no volume. Right? They were just, mathematically, they were just what in space? Dots. Point X, Y, Z. And it's moving from here to there, right? That's all they were, just dots. Okay, so we're going to make things a little bit better. The kinetic model of gases, Ellis. Okay, well, how did things improve? Not dots anymore. They're what? There's a hint. Yeah, they're heavy. Well, I don't know. I guess they have mass, but they're solid. They have some volume. They're what? What are these? Made out of steel. They're like steel balls. What's the technical word for collisions of steel? What type of collision? What was the word? Started with an E. Elastic, right? So that sound, these things don't get deformed, right? They don't get deformed. All that energy goes into what then? They collide. Nice, but where's the energy go? It can't go into reshaping these because they're elastic. Okay. Anna, I need your help. Yeah, come on up here. Okay. Oh, I get it. Wow, it was like one of those. Okay, anyway, let's go here. Let's go over here. Could have just left you where you're at. Okay, you got to hold this. I'm going to try not to hurt anybody. See if I... Now I can smell it. Can you smell it?
Wait. Yeah.
smells like what? What does it smell like on? Yeah, paper burning. All this energy goes into what? Heat, but not quite all of it, because you could hear it. So some of it went into sound, but pretty much energy goes into heat with these collisions. Okay, so they're elastic. Well, if they're solid spheres like this, according to the book, no internal modes of motion. Adriana, what's an internal mode of motion? Would this be an internal mode of motion?
Nothing's happening inside of the particles.
Yeah, so that wouldn't be internal. But nothing's happening inside of the particle. That's key, just what she said. Nothing's happening inside. Instrumental analysis, folks, raise your hand. Let everyone know who you are. Who's had instrumental analysis? Mad, raise your hand. All right? Instrumental analysis. Okay. What type of spectroscopy totally depended on internal modes of motion? What was it? You could Google it, and you come up with this. Infrared spectroscopy. Why? Because this is what's actually going on, right? A whole bunch of different vibrations. What are the black lines supposed to be? Bonds, all right? So this could be a big honking molecule, but the point is there's just several types of vibrations. Internal modes of motion. Can't happen with a what type of theory are we talking about now? Kinetic. Yeah, can't happen with the kinetic theory. That can't happen. So it's more real, but it's not real yet. Okay. We're getting better. At least things can collide now, and they have a mass. Root means square speed. How would you say that in English? Root means square speed. Everything is so abbreviated. The root means what? Square root. So the square, square. So the square root, mean. Layman's term, average. The square root of the average square speed of all the speeds, all the speed squared. You can't really, I don't know. I guess you could say in layman's terms speed times speed, but it doesn't really help, right? So the square root means square speed, c. It's the square root of the average of the speeds squared. So if you remember that, that's going to help you with a lot of homework, right? That will help you with a lot of homework. If I had, I don't know, let's say I have something that I can divide out. I have 10 cars. 6 are going 30 miles per hour north. That would leave 4. 4 going 50 miles an hour south, right? The root mean square speed, the square root of the mean of the speeds. How would you find C for those 10 cars? Alice, what would you do? You're on track here. What would you do? Square root of?
The average of all those. So, add them all together, say, 2.
Now, hang on. The square. I see the square root part. Then she's talking about adding them all together, right? I agree with that, but what are you going to be adding together? Okay, now we're getting into a word here, vector. Do we care about north-south? No, because we're doing speed. This isn't a vector. This is a speed. They don't care. This north-south thing, who cares? You don't even need it. Okay, go back. C, root mean square speed. Square root, big brackets. And then what are you going to be adding up? Okay, now you're getting there. Not 30 plus 30 plus 30 6 times, but 30 square root of the average of the speeds squared. 30 squared plus 30 squared 6 times plus 50 squared 4 times. The whole thing divided by what? 10. The square root of the average of the speed squared. Okay, then take the square root of that whole mess. Okay.
Can you get 30 plus 50 divided by 10? Oops, my bad, sorry. No, I'm just asking.
No. You see what?
I mean, you have the average, right? So you have to multiply the 6 and then divide it by 10.
Yeah, but I don't think you'd have to prove it to yourself on the calculator. It ain't gonna work because it has to be all these guys squared, right? It has to be that squared times 6. And you'd have to prove it to yourself on your calculator. It's the only way, I think. And then you got to take the square root of the whole thing. I guess I could finish this. 4 times 50 squared. Right? I divide it all by 10. Something like that. And you'd have to, Anna, put in what you said and see you get a different answer. All right, so that's kind of the idea what's going on there. Let's see. Oh, how about units? We go through all this. We get our C for our cars. What would be the units? What would be the units? Meters over second? That's the standard metric units for speed, but we didn't do any converting. So we're going to end up in what? Miles per hour. Fine, as long as they don't, standard, meters per second. That's fine. We'd end up in miles per hour. But since we're talking about gases, we're going to be talking about molecules and atoms flying all over the place. We're going to use this. Somebody did all the math for us. And they derive that relationship. We just need to know what it is. Well, the C is the same C. Now, though, we'll probably end up with what units for it? I would say meters per second. I don't know how we're going to get it, but I'd say meters per second. And then just put everything in standard metric units. So the 3 is, that's 3 is a 3. The R, which R would you pick to throw in there? There isn't an R with meters in it. No. There's no R with newtons in it. Which R is the standard metric unit R? Look at that inside front cover of the book. You got a bunch of R's. The one with joules in it. That's a big hint. The one with joules in it. Okay. Well, that means T has to be in Kelvin. To me, Sandy, the only question is that big M. What's the big M? Yeah, mass, but more specifically, the what of the gas? The molar mass of the gas. So, we find it on the periodic table, fine, but we better use what units for the molar mass, Amberly? Kilograms per mole. Make sure you convert it into kilograms per mole, and you'll be fine. Okay. Page 26 has something about Maxwell-Boltzmann distribution. What is it? Why did I say page 26? What was I thinking about? Is there anything in there that... Oh, okay. I think it's the plot. The plot, I guess I couldn't get on here for some reason, but... All right, the Maxwell-Boltzmann distribution. Just what's the fraction? That's really what f of v is. what's the fraction of molecules or atoms going at that speed v? And you can see how that fraction, right, changes overall, or how that distribution changes with temperature. Okay. So with low temp, which one are they really spread out, have a big range of speeds? The low temp or high temp? High temp, right? Because stuff's going to be going fast, stuff's going to be going slow. But if it's low temp, stuff can't be going fast. It's all going slow. That's really narrow. Same thing with really heavy stuff. It can't go that fast, so it's more narrow. Lighter stuff, all these speeds. Okay. So the Maxwell-Boltzmann distribution from the plot, right? You can see the fraction at that speed v, right? And multiply it times the speed, add them all up, you can get the mean speed of everything. Okay. So we've had the root mean square speed. We have some other speeds in here. The mean speed of these gases. Okay. If you're going to go back to the cars, Emily, go back to the car story. How would you calculate the mean speed? C bar. Can't use that equation, obviously, but what could you do? You hear what she's saying? Multiply the 6 times the 30 plus the 4 times the 50. Add them up, divide by 10. Yeah. Okay. How about Rob? How about mean? That's not up there, but I might as well add it. Mean velocity. So the same thing Emily said, but how do you take into account direction when you're doing all this?
I'd call north positive and south negative.
There you go. You have to do something. You have to make part of that problem. Okay, it doesn't really matter, but make sure you draw this and say, okay, I'm going to call that n, just following convention. Right? Usually n is up, and usually up is positive. Exactly, you'd have to do that. So then when you get an answer, it's negative. Well, that means overall it's going south. The overall motion of all these cars is south. Okay, most probable speed, C asterisk. Okay. Hey, what's this little pi thing? Go back to mean speed. It's just pi. It's just pi. Okay. So I'm glad we didn't have to derive all this stuff. The most probable speed of all this gases, of all their speeds. Relative speed. Okay. There's some different terms that they're going to be using in much more bigger and complicated equations. But we don't have an equation to get the most probable speed, right? That's easy for us to relate to with cars. So, I guess you'd have to get more into the statistics of it. We have Boltzmann constant. Just another constant. You look it up in the inside front cover. It's little k. But you can kind of tell what its units are going to be if you know what Na is. What's Na? I don't know why they use capital N. Usually they use little n. They're talking about gases and the number of moles of gas A. Usually it's little n. I don't know why they wrote big N. That's kind of confusing to me. But that's just the number of moles. So if R is joules per Kelvin mole, that has to equal, well, N is moles. That means K must have units of joules all over Kelvin. Yeah, so that'd be mole squared, right? But it's inside front cover, right? This is a number in its units. Just playing around. Okay. Do you remember using? Do you remember using reduced mass in physics, in general physics? I'm not sure which general physics it would be. But I just know you use stuff like F equals ma. Kinetic energy equals 1/2 mv squared. What's another one with m in it? Yeah, mv. That was momentum. So there's a lot of, in this Newtonian physics, you stick in that little m, right? And it's supposed to be what? Every single time? The mass of whatever it is that's flying around, right? Exactly. Makes sense so far? What if, now that makes total sense when all you have is this, right? I can throw it around and we can use F equals ma and all the equations we said that have little m in it. You just plop this on the scale and see what the mass is. What if we're starting getting closer to a molecule now? Atom A, atom B, right? There's some chemical bond in between there. The whole thing is supposed to be rigid, so I guess Rob, hold this guy, all right? Because they can't have any internal modes of vibration. So stick a steel beam or something, spread out a little bit more, solder it on there, right? So now you have that thing flying around. A big hunky mass here, a big hunky mass there. You know, just throw it across the room. Apply a force to it, whatever. Kinetic energy. What's the little m now? Before it was the mass of the object. What's the little m going to be now? It's not. Because what screws it up? What screws it up is, right? You can have all this twisting and stuff going on. Where is the... You want to treat... And you can still use Newtonian... The center of mass. You could still use Newtonian's equations and things. But you can't have... You have to take into account the center of mass. Here, there's no problem. The center of mass is in the center. So you just plug it on in, that's the mass. But now we need more like the center of mass. But more specifically... Where is it? Here it is. Reduced mass. Then we can use all these same equations. Wherever you see little m, now replace it with mu. You got it. That's the mu symbol. Okay? So how would you calculate little mu for this thing? How would you do it? Mass this one, put it in for m1. Mass this one, put it in for m2. I guess just see what these numbers are, add them up, then I'd push the 1/x button on the calculator, right, because it's in the denominator. Okay, and then you'd have it. And now you can use all the equations we used before. Wherever you see a little m, plug in a mu. Collision frequency. Collision frequency. So you have all, this room is full of these spheres, right, and they're flying around, hitting each other. You can calculate the collision frequency. What would be the units for z? Because that's what z is supposed to be. Z is supposed to be the collision frequency. Alice, what units would you slap on z? Now, the hint is frequency. In physics, what were the units for frequency every single time? Units. Oh, I can do this. Since you can bug me. Don't it? Don't it? Huh? This, don't it? Hertz, don't it? Right? Hertz. But, okay, what was really a hertz? What's a hertz? Yeah, well, per second. Now you can use the word cycle per second, repetition per second, but that's just, it's not there. It's always just 1/2. That's a hertz. Okay? So frequency, what per second? What's happening every second? How many per second? Collision. So collision frequency, it's really, the answer is really going to be per second. So it's just like cycles per second, repetitions per second. We stick in the word cycle or repetition. We have to stick in the word collision if you want to. But it's really per second, technically. So collisions per second. But you're not going to see collisions anywhere. But let's just write it in. Because when you start reading homework questions, oh, how many collisions per second? All right, well, collision frequency, Z. Okay. Now, how many collisions you get per second is directly proportional to C bar. Now, which one was C bar? Mean speed. Yeah, the average speed there. Does that make sense? You'd have more collisions per second if you crank up C bar. It's directly proportional. Because things are going faster, right? How about sigma? It's not even in there anywhere. Anna, what do you think sigma is?
Please don't say
Yeah, it's the diameter, right? The diameter of this molecule, right? So does that make sense? The larger this guy is in size, the more collisions you have per second? Yeah, right? I mean, he should be directly proportional. He should be on top. And how do you get this stuff? Oh, we're talking about argon, we're talking about neon, we're talking about helium. Where do you get this? You're going to have to Google it or find a table, right? Okay, so you can find that stuff. P. And it's also on top. I don't know if that's much of a hint, Mad. What's P? Pressure, right? Because the higher the pressure, the more collisions per second. What units, we should back up here. What units should we be plugging in for all this stuff? Back up to C bar, average speed. What units should we be using? Meters per second is what we better come up with. How about this diameter thing? Yeah, it better be meters. I bet you they're going to give you it in, yeah, I bet nanometers is a common number. Nanometers. Because what's the size of an atom? Really, really small. But 10 to the negative what meters? Size of an atom. Yeah, I guess. I'd say 10 to the negative 10 about. Yeah, kind of like 10 to the negative 10. So very common to describe sizes of things on the atomic size are nanometers. So how many nanometers in a meter? You're going to have to need to know it, because I bet you the tables are nanometers. I'm just guessing, but I bet you they are. If it's anything else, you just Google it. But what's 1 times 10 to the negative 9 meters is 1 nanometer. Or 1 times 10 to the 9 nanometers is 1 meter. Right. Okay, so we're here so far. So make sure you convert him into meters. How about that K? We said that was Boltzmann constant. Look inside front cover. T? Temperature, Kelvin. Does it make sense that T's in the denominator?
yes.
If you crank up the temperature, would you have more or less collisions? Go back. We said the ideal gas law. We said that thing works when the temperature is really, really what? It works the best. I mean, you can use PV equals nRT to predict whatever temperature you want, but it's going to give better results when the temperature is really, really high, hot, warm. Because then what?
It's more ideal.
Yeah, it's more ideal. They're more acting like dots. To me, the only way to figure this out, because you'd think things are flying around faster, there's more higher odds of them colliding, right? But I think you got to think of it how it doesn't work. When things start interacting with a gas, what's the word? Sort of the C. Right? Because you don't want ideal gases. They can't do this. They can't interact. They can't make a liquid. Can't condense. They can't condense. When do things condense? When the temperature is really, really cold, right? Yeah, low. And then things start condensing. You start getting these interactions. That's very non-ideal behavior. So I think you want to think of it this way. They're colliding and sticking together somehow. It's more than, I don't know. That's the only way I can think of this, is when I hear things flying around really fast, the number of collisions per second should be going up. But it's not. All right? They're going, so really a collision must be more like let's say they're going to miss, right? But if you slow down, slow motion photography, all right? They must not be in the real world straight paths. What's the A word? Stuff attracts, right? And they get close enough together, they're going to repel. But stuff attracts stuff. So these aren't going to be straight lines. They're going to be more arcs. Right? How do I draw an arc? That guy, he has to go down while he goes up. So you have to be music, like percussionists can do two different things with their hands. But this guy has to go down. See what I'm trying to do? Yeah. But, I don't know. But, all right, arc and arc up, attract. So I think that's what's really going on. That's why T has to be indirectly proportional. Higher the temperature, dang, all right, you're going to have less collisions. Lower temperature, more collisions. You get condensation even. Mean free path. You take C bar, that mean speed, divide it by Z, which we said is collision frequency, and you get mean free path. What's mean free path? Adriana, what's mean free path? To me, the only hint I can give you is path, but we're talking about collisions. So it's pretty much just the average distance between collisions. So if the mean free path is really, really large, would that be a really low pressure or really high pressure? If that mean free path is huge, really, really low pressure. That's what you have to use in that instrument upstairs called the mass spectrometer. Gas actually has to go from this end to that end, physically, this far. These atoms have to go from, these molecules have to go from here to here. They got to get there. The only way to get there is to collide with nothing. Nothing. So you have to have a vacuum. You have to have really, really low pressure to get from there to there. That mean free path has to be this big. It's huge. Okay. So that's some stuff. I think we're about done, right? Yep, we're done. Okay. Let's do problem, I have marked down. I want to do problem 112 first, because I think that's the hardest one. Problem 1.12, let's do that first. Okay. So read it over. Cars were timed by police radars. They passed in both directions below a bridge. Their velocities, kilometers per hour. Lost my pen. Number of cars in parentheses to the east and west were as follows. 80 east, right? So 80 kilometers per hour, 40 of them going 80 kilometers per hour east, 62 going 85 kilometers per hour east, and so on. What are A, the mean velocity, mean speed, root mean square speed? Mean velocity. So to get that one, Sandy, well, Rob gave us a hint, if you remember it. What would you do? Use the vectors. So let's draw a little, what would you call it, a legend or something, right? East and west is usually that way and that way. What's west? West is usually over here, isn't it? Just by convention. You don't have to use convention, but you have to say what's plus and what's minus. So typically, right, east would be positive, that would be negative. So to get the mean velocity, how would you start setting this up? like the 40 of them going 80 kilometers per hour east. What would you write? Positive or negative 80? Positive 80. All right. And how many of them? 40. And then you just keep adding them all up. All right. And you do that for every single one. If it's going west, make it a negative sign. Divide it by, I don't know, whatever that total is. They never even told you it's the total. Do we need to convert all this stuff to meters per second? Yeah, I mean, they didn't say give you an answer in meters per second, so we're going to give it in kilometers per hour. Why do all that converting if you don't have to? And just keep going. Okay. Now, I say you see how to set up A, right? Didn't we figure we're going to do this? We're going to jump to the next one after you know how to set it up. Okay. How would you set up B then? How would you set up B, Kathleen? How would you set up B? Now, they want in B, they want the mean speed. There you go. Exactly. Did you hear what she said? The exact same thing, just don't have any negatives. Exactly. Same thing, but no negatives. Okay. And we have the root mean square speed. Amberly, how would you start setting this one up? The root mean square speed. Okay, a big square root thing.
And then you would have similar to B, but squared the 80, 85, 90.
Square all the speeds. You hear what she's saying? Exactly. Very similar to B. Really, it doesn't matter whether you have negative signs in there or not because you're going to square them. They're going to disappear on you. But square all the speeds, she's saying. Exactly. That's pretty much it. So you'll have the denominator, the total number of cars. On top, what do we have? 40 times 80 kilometers per hour squared plus, and you just keep going. 62, 85. Okay. All right, comfortable with it? Let's check out, now let's jump up to the top and do 1.13. They want us to find the ratio of the mean speeds of hydrogen to mercury atoms. Okay. We need an equation for this, right? Mean speed of atoms. Where was that? What symbol was that? That was C bar, right? So we really want C bar of hydrogen all over C bar of mercury. Man, wouldn't it be nice if a lot of stuff canceled? But I doubt if it will. You never know. We'll find out. Right? So we'll find C bar of hydrogen divided by C bar of mercury. Some stuff might cancel. That would make life a lot easier. Right? Let's plug it in. C bar, we said, was 8 RT over pi m square root. That's inside a square root. It's going to get hard to cancel anything. What did I say? 8 RT. Yeah, I don't think we're going to cancel it. At least I'm not going to mess with trying to cancel stuff. It's not worth the trouble, don't you think? Well, that's not so bad. Just make sure big M is in what units? Kilograms per mole. That's not so bad. Let's check out B. The mean kinetic energies of hydrogen to mercury. Kinetic energy of hydrogen. Kinetic energy. Mercury. Atoms. Okay. What was the equation, Emily, for kinetic energy? 1/2 m what? V squared. Okay, so our little m has to be the mass of what then? Hydrogen. How many of them? Oh yeah, sorry. How many molecules of hydrogen? 1 molecule of hydrogen, 2 atoms of hydrogen, right? So it's going to be the mass of a hydrogen atom, right? The speed of that hydrogen atom. 1/2 the mass of a mercury atom, the speed of that mercury atom squared. Now where do we get these speeds from? And then square them? Where do we get those from? From part A. Yeah, we did it. We found the average speed of hydrogen, right? So just have to square it is all. We found the average speed of hydrogen. Just have to square it. Right? Make sure you square it. It's a good thing we didn't go through all the work of trying to cancel stuff. Okay, how do you find the mass of a single molecule? What's the trick to doing that? Hydrogen, for example. How do you find the mass of a single molecule? Well, 1.00794 is the mass of hydrogen. I guess the molar mass of H2 would be 2.0, right? But that's not the mass of 1. Google. Yeah, but on a test or an exam, you can't Google. No chart. There's not going to be a chart. The hint, there it is. The hint is Avogadro. If you find the molar mass of hydrogen, H2, you just find it on the periodic table. But that's the mass of how many atoms? Avogadro, which is how many? 6.022 to the 10 to the 23rd. So if you want to find the mass of 1, divide what by what? Divide what? Divide that molar mass by Avogadro. Right. So 2.014 or something, right? Find the exact molar mass. Divided by Avogadro, you'd have the mass of 1. Same thing for mercury. I don't even see where Hg is. Where is it? It's a heavy. Where is that? Oh, there it is, number 80. Right? Number 80. So how do you find the mass of 1 mercury atom? Divide 200.59 by 6.022 to the 10 to the 23rd. Okay. You're still going to be wrong. Why? Now, in this case, you could get by with it. What units does kinetic energy should have? What units? Joules. So that means little m's had better be in kilograms. Speed had better be in meters per second. So make sure speed is in meters per second squared. But in this case, if you forgot to convert, do you realize you get by with it? I mean, you shouldn't. Even though it's extra work, I would still convert because then you'll never screw up. But your conversion factors cancel. So you can get by with it here. But okay, a few more minutes here. How about any questions on 13? How about 14? A glass bulb contains 1 times 10 to the 23rd hydrogen molecules. If the pressure exerted by the gas is 100 kilopascals, what's the temperature of the gas? What would you use to get that? They gave you the number of molecules. They gave you the pressure. Oh, and they gave you 1 liter, too, so they gave you volume. Any idea? You don't have much choice. Whose law? They didn't say it was this type of gas, but ideal gas law. You have no choice. Even though we're talking about kinetic theory, we don't have any choice. I mean, they didn't give us a equation of state with the kinetic theory of gases. So we have to go back to the ideal gas law equation of state. Well, that's fine. Okay, so I would use that for part A. And then part B. The root mean square speeds of the molecules. Oh, we have an equation for that, right? Okay. So in B, you probably just use the equation. Would the would the temperature be different if they were oxygen molecules? Would the temperature be different if they were oxygen molecules? Different molar mass. Yeah, you have to go back to part A. How did you get part A? You just found the number of moles. You didn't care what it was. You just used Avogadro's number, right, to get it into moles? In part A, you see that? So you use Avogadro's number to get into moles, to get your little n, then you calculate your T. You don't care what type of gas it is.
Isn't that already the number of molecules? So we really have to use that?
Oh, little n isn't the number of molecules. Little n's the number of moles. Oh, I'm glad somebody asked that. That you have to convert to moles. Get that, right? And you get little n, which goes right there. Right? Use Avogadro to convert. Now, I don't see how it would affect it, right? It can't. Can it affect the answer to B, though? Why? It would, you're right. It would change what? Specifically. Yeah, you have to go back to that C-bar equation. See what it would change. Big M is in there. Ah, definitely different. Okay, so we're about out of time, but I think you have a shot at all of these. So look at the next one, mean free path. Just use the equation. Watch your units. So come by if you have some questions.